Welcome to This Explainer. Today we're tackling one of history's absolute coolest scientific mysteries, and we're doing it with nothing but a wire, gravity, and a ridiculously heavy brass bob. Seriously, have you ever stopped to think about the fact that right now as you listen to this, you are literally spinning on a giant rock at over 1,000 miles an hour? It's kind of a mind-bending reality, right? We totally take it for granted today, but proving this hidden spin, actually proving that the solid ground beneath our feet is moving, well, that was once a monumental challenge for science.
So let's dive into this seemingly simple but historically profound question that literally stumped humanity for centuries. I mean, if you look up to the sky, you see the sun, the moon, the stars, they're all moving across the horizon. But how do you know they are the ones moving? What if it's us? How do you prove the Earth is rotating without using the heavens as your cheat sheet? We needed a way to prove our outward motion while looking strictly inward, right here on the surface. Scientists knew the math demanded it, but they couldn't point to a single earthly experiment to actually prove it.
Here's our roadmap for today. We'll start with the grand scientific question, then look at Foucault's famous 1851 experiment, break down exactly how the pendulum works, dive into the underlying physics, and finally, we'll wrap up with the latitude challenge.
Part 1. The grand scientific question. Looking inward to prove outward motion.
Part 2. Foucault's 1851 experiment, a spectacular demonstration in Paris.
And that brings us to Leon Foucault. He was this incredibly clever French physicist who realized, hey, I don't need to look out into the cosmos to answer this riddle. He figured out how to demonstrate our planet's motion using only the fundamental laws of mechanics. He created a setup so elegant, so perfectly simple, that it's actually still replicated in science museums all over the world today.
Now, the sheer immense scale of his setup is what really made it a spectacle. Foucault didn't just build some tiny desktop model. No, he went big. He suspended a 67-meter-long wire, that is over 200 feet by the way, right inside the Pantheon in Paris. At the bottom, he hung this massive, heavy brass bob, dangling over a beautifully numbered dial on the floor. And then, he just invited the public and the scientific community to come in and watch it swing.
As those Parisian crowds gathered around, they witnessed something absolutely extraordinary. The pendulum didn't just swing back and forth in a static line. Over time, the plane of oscillation appeared to slowly rotate relative to the Earth beneath it. It was just ticking its way around that dial, hour by hour. This was huge. It provided one of the very first direct experimental demonstrations that the Earth actually rotates on its axis.
Part 3. How the pendulum works, breaking down the motion step by step. So what was actually happening mechanically to make this happen? Well, step 1 is all about the setup. The pendulum is carefully pulled back and released without any sideways push at all, just a clean drop. Then, step 2, thanks to inertia, the pendulum simply wants to keep swinging in that exact same plane in space. It doesn't want to turn. But step 3, this is where the magic happens. The Earth itself is literally rotating beneath it. So to an observer standing on the floor, the swing plane appears to rotate. But in reality, the pendulum is fixed. It's the building that's moving.
When you look at the dual perspective of this, it's pretty mind-blowing. From our ground perspective, say over a 5-hour period, the swing line seems to twist clockwise. We swear the pendulum is changing direction, but a top-down view reveals the incredible truth. The pendulum is faithfully swinging along its exact original line in space. It hasn't turned at all. It's the Earth that is twisting underneath it.
Part 4. The underlying physics. Taking a look at the unseen forces driving the phenomenon.
To truly grasp this elegant illusion, we really have to look at the masterclass in classical mechanics that's running the show here. The whole thing relies on inertia, keeping the bob steady in its fixed plane, while the Earth's literal rotation creates what we call a rotating reference frame. Because we are moving with the Earth, we experience this conceptually as the Coriolis effect. That is what makes that perfectly straight swinging pendulum appear to curve over time.
And of course, the crucial point comes down to the math. The formula here shows that the angular speed of the pendulum's apparent rotation, which we call omega, equals the Earth's angular velocity multiplied by the sine of your latitude. So what does this actually mean for us? Well, mathematics is literally telling us that this rotation effect completely changes depending on how far north or south you are on the planet.
Which brings us to Part 5, the latitude challenge, testing your understanding.
Since Foucault noted that the apparent rotation depends so heavily on where you set the experiment up, I want you to try a thought experiment. Imagine placing one pendulum way up at the North Pole and another perfectly on the equator. Now, at the North Pole, the pendulum completes a full 360-degree rotation in exactly 24 hours. But down at the equator, there is absolutely zero apparent rotation. It just swings in a straight line forever. So why are they so drastically different?
Well, think about how Earth's rotation axis is oriented relative to each specific location. Up at the North Pole, the floor is essentially spinning horizontally, kind of like a record player right underneath the pendulum. But down at the equator, the floor is moving straight ahead through space in the exact same direction as the Earth's rotation, meaning the floor doesn't twist beneath the pendulum at all. If you can picture the orientation of the ground beneath your feet right now, you just might crack the code to our planet's hidden spin. So what do you think? If you set up a pendulum in your own hometown, how long would it take to make a full circle? Keep observing, keep questioning, and I'll catch you in the next explainer.